This lesson is on binding energy per nucleon, and here are your objectives. Here we have a stationary helium nucleus, and we want to separate it into separate stationary nucleons. In order to do that, we have to put in energy, because the helium nucleus, when it's intact, is a more stable state than those separate nucleons. Now, remember from Einstein's famous equation, E is equal to mc squared, we said that mass and energy are two sides of the same coin. So if we put in energy here, then the products in this reaction are going to be more massive. There is more mass on the right-hand side than on the left-hand side. If we were able to measure the mass of the separate nucleons, we'd get a greater sum total mass than the mass of this helium nucleus. That's where this energy goes. This energy we call the binding energy. It's the energy that you need to put in order to separate an intact nucleus into its separate nucleons. And that binding energy shows up as the greater mass of the separate nucleons. Remember, with E is equal to mc squared, now we can no longer talk about conservation of mass or conservation of energy separately. We talk about them together. So if I look at the mass and energy on the left side here, including the mass of the intact helium nucleus and this binding energy, that's equal to the sum of the mass and energy here on the right-hand side. So this side has to have more mass. Now we can run this in the opposite direction as well and take the separate nucleons and bind them into a helium nucleus, and that would release the binding energy. So equivalently to the situation above, creating a nucleus out of its separate nucleons releases the binding energy. Now over here we have less mass. And again, if we take the mass on the right-hand side and the binding energy, that's got to be equal to the mass and energy on the left-hand side. We call the difference in mass, the missing mass, the mass defect. And so the mass defect, the amount by which the mass over here on the right-hand side is less than the mass on the right, that's the mass defect. That mass defect is equivalent to the binding energy. And that gives us a way of working out the binding energy. We figure out the mass defect and then use mass energy equivalents to work out what the binding energy was. Let's take a look at an example. We'll find the binding energy of carbon-12. So what am I going to assemble together to make carbon-12? Well, I'm going to take 6 protons and electrons and 6 neutrons. That's what's going to be on the left side of my equation. So the mass of 6 hydrogen atoms, and this is a complete hydrogen atom with a proton and an electron, and I want to use that in order to make sure that I also capture the mass of the electrons. The mass of 6 hydrogen atoms would be 6 times the mass of 1, and we look that up and we get in atomic mass units that the mass of a hydrogen atom with a proton and an electron is this many atomic mass units. So I've got 6 of them, so I multiply by 6. Then I look up the mass of neutrons in atomic mass units, and I see that's 1.008665 atomic mass units, and I've got 6 of them. So that's what I have on the left side of my equation as I'm assembling my carbon-12 atom. On the right side, I have the carbon-12 atom itself, and we know that by definition, the mass of a carbon-12 atom is exactly 12 atomic mass units. So I'm going to write that with the same number of decimal places as I have here. And so that's the right side of my equation, the products. Now what I have to do is subtract them to find out the missing mass, the mass that has disappeared as I go from the left to the right side of the equation. So I multiply and then I subtract, and I get 0.098940 atomic mass units have gone missing. That's my mass defect, by how much the right-hand side of this equation is less in mass than the left side. So now that mass defect, we said, is equivalent to the binding energy. So I take my 0.098940 atomic mass units, and I use my equivalents of mass and energy. Now, instead of using E is equal to mc squared, converting this to kilograms and putting it through E is equal to mc squared, I'm going to use the value that I worked out in the previous lesson, which is that 931.5 mega electron volts is the amount of energy we get out from one atomic mass unit. So now I just multiply this across, and I get approximately 92.16 mega electron volts. Again, what I've done is I've figured out the mass defect, and then using this relationship that one atomic mass unit, when it disappears, releases 931.5 mega electron volts. We worked that out in the previous lesson from E is equal to mc squared. I get this as the total binding energy. That's how much energy is released when we construct a carbon-12 nucleus from its constituent nucleons, and by the same token, it's the amount of energy we'd have to put in to separate that carbon-12 nucleus out into protons and neutrons. Now, this is the total binding energy, but we can also work out the binding energy per nucleon. If we take 92.16 mega electron volts and we divide by the 12 nucleons that we have in that carbon-12 nucleus, we get approximately 7.7 mega electron volts per nucleon. We call that the binding energy per nucleon, and that gives us a measure of stability of the carbon-12 nucleus. The higher this number is, the more energy needs to be put in to separate out a nucleon from the nucleus, the more stable the nucleus is. And further, by standardizing in this way, by finding the binding energy per nucleon, we can now compare stability amongst different nuclei, even though they have different numbers of nucleons. The higher the binding energy per nucleon for a nucleus, the more stable it is. So if we work out the binding energy per nucleon for different nuclei and we graph them with number of nucleons, in other words the mass number here going up to the right, and binding energy per nucleon going up here on the y-axis, then we can compare stability amongst different nuclei. Again, as the binding energy per nucleon goes up, we're getting more stable nuclei. So more stable nuclei are going to be towards the top of this graph. And what we see is that the values increase sharply and then they kind of plateau like this and come down slightly. What this means is that our most stable nuclei are up here. And up here is where you'll find iron and nickel. Iron with 56 nucleons and nickel with 62. These are our most stable nuclei. Up here, they have the most binding energy per nucleon. Again, that means you need to put the most energy in to these per nucleon to separate out a nucleon from the nucleus. This graph also tells us that if we can take larger nuclei than iron and nickel and split them up, and we call that fission, then we can get out more stable nuclei, and with that we'll get a release of energy. Splitting up larger nuclei, larger than iron and nickel, will allow us to make more stable nuclei, and that will release energy in the process. And that's called fission, and that's how nuclear reactors work, by splitting things like uranium. In contrast, if we take smaller nuclei and we can get them to fuse together, and this process is called fusion, then we can create larger nuclei that again have a higher binding energy per nucleon, are more stable. And this is the way the sun operates. It fuses hydrogen into helium with a resultant release of a lot of energy. In both fission and fusion, the products have a higher binding energy per nucleon than the reactants did. That means they're more stable. They're further towards the top of this graph. It also means that the products have less total mass than the reactants did. You can think of this graph as also showing that as you move up, you have less mass per nucleon. If you divide the total mass of an iron nucleus by the number of nucleons, you get a lower number than something over here or over here, like uranium. So as you move towards the top of the graph, you get less mass per nucleon, higher binding energy per nucleon, and that difference in binding energy is the energy that is released in the reaction. So binding energy per nucleon allows us to think about nuclear stability and also helps us to understand where energy comes from in reactions like fission and fusion.